It is a section 4.4, invertible matrices. On n by n, square matrix A is invertible or non-singular if that is on n by n matrix B such that both AB and BA are the identity matrix. In this case, by using advanced theory of linear algebra, we can prove that such B is unique. So we can say B is the unique inverse of A, and we are using the notation A inverse. So this equation can be written here. A inverse is the identity matrix, and it's the same as A inverse A. See this example. A and B are given, and we have to find AB and BA. Okay. Here AB. Okay, for that one. Here A and B. Row, column. First row, first column. That is minus 14 plus 35. The first row, second column. Minus 10 plus 10. And now here, second row, first column, 21 minus 21. And second row, second column, and plus 15 minus 14. So we can see here now, okay, this one is 14, okay, that must be 15. So that is 1, 0, 0, 1, which is the identity matrix in 2 dimensions. Okay, how about BA? Okay, that is, okay, we write down here B first. Minus 7, minus 5, 3, 2. And A is 2, 5, minus 3, minus 7. Okay. Then, first row, first column, that is now minus 14 plus 15, so that is 1. First row, second column, is minus 35 plus 35, that is 0. Now here, second row, first column, plus 6 minus 6, which is 0. And second row, second column, 15 minus 14, which is 1. So here we checked that AB and BA are the identity matrix. So A is inverse of A, inverse of B, and we can say B is the inverse of A. Either way, you can say that. Inverse of on n by n matrix, for n is larger than or equal to. On n by n square matrix, A is invertible if and only if A is row equivalent to the identity matrix. That means that start from A, if you apply elementary row operations, then its reduced echelon form is identity matrix. That is also the same as there are n pivot positions. So each row and each column has a pivot position. In this case, any sequence of elementary row operations that reduces A into the identity matrix will also reduce the identity matrix to A inverse. Okay, this observation is introducing an algorithm to find A inverse. Start with this augmented matrix, A and identity, and we apply elementary row operations so that we'll try to make the first part to the identity matrix. We already know that A is invertible, then we can apply elementary row operations to reach at the identity matrix. So once we do that, then this identity part will be changed into the inverse of A. Once we cannot reach at the identity matrix for the first portion, then A does not have any inverse, which means that A is not invertible. That is quite similar as this one. Once we try to solve AX equals B, and here once A is invertible, which means that there are n pivot positions, then from this augmented matrix, after applying elementary row operations, we can reach the identity matrix, and the extra column will be the solution X, which is the same as here, A inverse times B. So we start with B over there. If we start with, for example, identity matrix, then there will be here exactly this portion will be A inverse, right? Okay. Okay, find the inverse of A. A is given here. Now, we may begin with this augmented matrix, the matrix and identity. From here, now, okay. Now, we have to apply elementary row operations such that and this portion becomes identity. Okay, we may try to use non-integer computation to avoid that. Okay, let's try to do this way. First, we multiply 3 for the first row, so that there is 9 and 6 and 3 and 0. For this one, we try to eliminate second row. Then there will be 1 and 1 and 3 and minus 1, right? Okay, second row is subtracted, is 1, 3, and minus 1. Okay, and then we put here the second row, 8, 5, 0, 1. That's a kind of a replacement. Okay, now from here, we can eliminate the second row, and without introducing non-integer values, 1, 1, 3, minus 1. Okay, 8 times subtraction, which will be 0. 8 times subtraction, minus 3. 8 times subtraction, minus 24. 8 times subtraction, so 8 is added, which becomes here now 9. Okay, yeah, divided by minus 3, which becomes here, that is 0, 1, divided by minus 3, so 8, and minus 3, right? So by using this one, this PV value, we can eliminate that one by subtracting the second row. Okay, so it is a 1, 0 subtraction, and minus 5, and subtraction will become here now 2, right? Okay, now we are putting here 0, 1. Okay, is it 2, minus 5, and subtraction the same as adding 3, so it's 2. Okay, yes, correct. And that is 8, and here minus 3. So now it becomes identity, and so that this portion will be A inverse, right? Okay, now we'll go to here, and it's for your self study. Use pencil and paper to find the inverse of A. If it exists, we can check the existence of inverse by using MathTalent. We define A, and now I, 3, that is making 3 by 3 identity matrix. So we form the augmented matrix and try to reduce the echelon form. So first part becomes identity. Now this portion is A inverse. Just by using pencil and paper, try to check it. Okay. Okay. Given on n by n matrix A, it doesn't have to be square matrix. The transpose of A is the matrix here using the notation A transpose, whose columns are formed from the corresponding rows of A. That means that here A is Aij, then in Rmn, then A transpose is now, rather than Ij, we are putting Ji, and that must be in R n by m. For example, here A is given in this way, then A transpose. Okay, in definition, we say that here the columns are formed from the corresponding rows of A, and each column in A transpose is formed from rows, which means first row goes the first column, 1, 4, A1. Second row goes to the second column, 0, -2, -1, and 3. Third row goes to third column, 0, 9, 9, 0, okay, 9, 0, 0, 5. Okay. And this row goes to column. Or you can say that first row goes to the first column, second row, second column, third row, third column, third row, the final column, final row. You may think of that way. Either way, they are the same. Okay. Here we have properties of invertible matrices. Okay, for 2 by 2 matrices, we may write the matrix in this form A, B, C, D. If AD minus BC is non-zero, then the matrix A is invertible, and A inverse can be written in this way, 1 over AD minus BC. In the next section, we'll learn about determinant, and this is a determinant. AD minus BC is a determinant of the matrix. Once it's non-zero, then we put here 1 over the determinant, AD minus BC, and from the matrix, here we change the position, AD are interchanged through this cross direction, and here for the other direction, now change the sign. So change the position, change the sign. Okay, and in front of that we have 1 over AD minus BC. That's the inverse of given matrix. So as far as AD minus BC is non-zero, and we can form this matrix. Okay, so it is invertible. If A is an invertible matrix in general dimension, then A inverse is also invertible, and inverse will become the original one. It's reasonable, right? If AB are n by n invertible matrices, then their product is also invertible, and the inverse of AB is the same as B inverse, A inverse. Be careful, you have to change the order, AB, but here B inverse, A inverse. Okay. We'll not prove that, but it's well known fact. If A is invertible, then its transpose is also invertible, and transpose and inverse commute, so that you can get inverse first and transpose, or transpose first and inverse. if A is an n by n invertible matrix, then for each B, for any choice of B, okay, that means for each B, the equation AX equals B has unique solution, so that X must be A inverse of B. Okay, for every choice, it has unique solution, means that here, if you start with augmented matrix, then for every choice of B has unique solution, means that, and every column of A has a PB position. So the columns of A must be linearly independent, right? We'll see later, they are basically the same, the assertions. Okay, that is the invertible matrix theorem. A is an n by n square matrix, then following are equivalent. This is an equivalent theorem for invertible matrices, and originally the invertibility is defined in this way. In definition, by definition, here we need a matrix such that AB and BA are the identity matrix. So it is not easy to verify this definition. Now we will put here the equivalent statement so that if you can verify one of these statements, then that means that the given matrix is invertible matrix, right? So equivalent theorem is a kind of expansion of the definition. Okay, A is an invertible matrix, then A has row equivalent to the n by n identity matrix. We considered it earlier, and that is also same as A has n pivot positions, and so that this homogeneous equation should have only the trivial solution, and columns of A must be linearly independent. And so we collect the findings in earlier here. Okay, we consider the matrix multiplication as linear transformation, then it is a one-to-one. We didn't study about the one-to-one, but here that is quite similar concept as the one-to-one when you are dealing with the standard function of one variable. So you may think of that way. This is one-to-one. And also, now this equation has unique solution for every choice of B, and we also consider this one. And the columns of A span Rn, okay, so that the linear combinations of the columns of A will make every vector in Rn. That one is basically the same as that one. For every choice of B, we can produce B as a linear combination of columns of A. That is exactly the same as that one. Now also, if we consider this one as a linear transformation, there's onto, which means that the image under the multiplication of A is now the same as the whole space, which means that, and here for each one in Rn, we can make it. So that one is the same as this statement. Okay. There is a matrix C such that CA is identity. Original definition of invertible matrix is existence of a matrix such that right multiplication, left multiplication are simultaneously the identity matrix. But here, this statement is saying that just left multiplication becomes identity, then that's enough. And so that means once left inverse exists, then it becomes automatically right inverse. Okay, here again, now this is a right inverse, and once right inverse exists, then the right inverse will become also left inverse. So only one side inverse is enough here, and A transpose is invertible. So once A is invertible, then A transpose is invertible. If A transpose is invertible, then A itself is invertible, and this is already we considered inverse and transpose commute. Okay, more statement will be added in the coming sections. Here we'll see more the equivalent statement later on. AB are square matrices. If AB is the identity, then A and B are both invertible. So we can say that B is A inverse or A is B inverse. Right? So the definition of inverse is also a sort of a symmetric definition. Use the invertible matrix theorem to decide if A is invertible. Once you verify one of these statements, then that's it. Okay, here let's try to use this one. So most frequently used statements will be this one, and also that one, and here probably also this one, and also that G. Okay, so for this problem we'll try to use that, so that the problem is reduced to checking the number of pivots. Right? Okay, from A, now we apply elementary row operations. So 1, 0, 2, the first row is not changing. And then here, 3 times subtraction will make a 0. 3 times subtraction the same, 1, because it's 0. 3 times subtraction, 6 is added, so it will become 4. And 5 times addition is 0. 5 addition minus 1. 5 times addition, that must be here, okay, minus 10, so that it is a minus 1, right? Okay, from here, again, along with this pivot, we can make it 0, 1, 0, 2. Anyway, you have to reach at on echelon form. Okay. So it's a 0, 1, 4, and addition 0, 0, and 3. We have 3 pivots, okay, on echelon form. So the columns are linearly independent, which means that the matrix is invertible, right? Okay. That's the end of the section. Thank you.